If you don't want your face seen, turn your camera off. We've got what's going to be a kind of different one today for the APGC seminar. So we've got Duke Pauli. And what I'll do is I'll direct you to his website in the chat, because there's a great video that's worth watching later of his robot systems. It's well worth watching, what we were chatting about. So Duke's assistant professor at the School of Plant Sciences in the University of Arizona. And there he's looking at trying to tease apart genetics of abiotic stress tolerance, specifically heat and dry, since it's in Arizona. He's got an excellent background. So he had a PhD in plant sciences from Montana, where he was, it was more around looking at the genomic assisted breeding, looking for superior malting barley. And thanks to Robbie for identifying Duke as a speaker here. So that's a nice International Barley Hub APGC link there. So we're linking the scientists we talked to. And so in Cornell and now in his post now, it's much more looking at high throughput phenotyping technologies. And he's probably going to tell us about some of the horror stories of going down this route, I think, which is good for us because we're building our own phenotyping center. Nothing of the scale you're talking about, or size, physical size, scale maybe. So we're looking forward to hearing about your adventures in phenotyping, to be honest, Duke. So I'll let you go. I'll let you start.
All right, can you see my perfect? Okay. First of all, thank you for the invitation to present some of this work. It's a real privilege and an honor. I've seen some of the other speakers in your series, and they're all very impressive. So really just a great opportunity. As Derek said, I'm going to talk about something a little bit different than perhaps you're used to, and I'm going to try and make the presentation somewhat shorter because it's about data processing, which always is not the most exciting thing, but hopefully there'll be a lot of time for questions, and I can tell you more about the horror stories that Derek alluded to. So there's a large team of people behind this, but there's always kind of one person that shoulders a lot of the burden, and that's a phenomenal grad student I have. His name is Emmanuel Gonzalez. He's just been phenomenal. Before he started grad school, he had no computer programming experience and went from 0 to hero in about 3 months to writing a majority of the pipeline that you'll see today. So as Derek said, my research programs primarily focus on abiotic stress in crop plants. And I was fortunate that when I moved to Arizona, I had the opportunity to get involved with this unique project. So I think one thing that's common, we all know, is that emerging technologies have really democratized data collection. It was 2011 when Verbeek and Tester wrote that paper about phenomics and relieving the phenotyping bottleneck. Although, hardware did kind of relieve that bottleneck, I feel like it just created a new one. So now we have lots of platforms for collecting data, from robots to mobile carts in the field. The most common one, I feel like, drone technology and even phones. And so now basically it's really cheap and easy to generate a lot of data. And although this is great, it often leads to the problem of, so once you have that data, how do we turn it into something meaningful, some knowledge, insight that we can actually do science with? So prior to 2018, when I started as an assistant professor, I had limited experience. But when I got there, I was 6 months on the job when I was asked to take over and be the area PI for this project. And quickly identified that, wow, this giant robot is massive. So here's an image of it. As I was telling Derek, it's about 70 feet tall to the top of that cross member. It has a sensor box, and I'll show that in detail. But basically, this is a giant robot. This thing works around the clock, 24 hours a day, 7 days a week, scanning the field. We do, have an extreme environment, so that does have some constraints. But the biggest thing here is that with this type of technology, the data volumes have gotten just, well, pretty massive. So this graph right here just shows that, at approximately 1 month of scanning, we're generating 21.5 terabytes of data for our lettuce that we grow in the winter, and about 40 terabytes on our sorghum when we're growing it in the summer. This excludes our hyperspectral camera. Our hyperspectral cameras generate a whole boatload of data. And so oftentimes we don't always run those. And so if you think about this is per month over a 3-month growing season, the numbers quickly add up. So just some brief history about the gantry. It was constructed in 2016. Arizona was selected mainly for its cloud-free weather. We have a year-round growing season, but we also have a very unique environment. You know, it's hot, dry most of the time. Even our winters are pretty mild and warm. But more importantly, I always tell people that, you know, Arizona has the climate of tomorrow. Today, you know, as we think about climate change and what that's going to look like, we are actively confronting a lot of those challenges right now. Specifically, you know, right now the water cuts are hitting the Colorado River, and so growers in our area have already lost a third of their allocated water. So this project was funded by the Department of Energy Advanced Research Project Agency for Energy. It was mainly constructed for studying bioenergy sorghum. When Lenatech sold them the package, they were told they were buying something that was turnkey, that basically they were going to build this, and as soon as it was up and running, they'd be getting phenotype data. So about in 2018, the field was expanded, so more rails were put in, and now it added an additional 1 acre of land to the scannable area. So now it's just about 1 hectare, about 2 acres. And the north field, which we call it, is for growing grain sorghum. So crops that we have grown on there include sorghum, wheat, sunflower, and lettuce. You can tell that most of those, the wheat and lettuce, are our winter crops, and sorghum, sunflower we do in the summer. So yeah, as I said, when I took over in 2018, bright-eyed assistant professor, I was asked to join this project and take over, and noticed that there were some significant issues. I guess the best one that can encapsulate it is, prior to this, the data processing took 9 months. And unfortunately, in one instance, it took 9 months for them to realize that they had left the lens cap on the thermal camera and basically, you know, didn't collect a single thermal image. So that was my nightmare scenario. And so one of the first things I realized was that we needed to have some type of analytical pipeline that could more fast, you know, quickly and efficiently process these data. And this kind of began my journey into, I guess, more of the data aspect of phenomics, because prior to that, I was mainly on the genetics component. So here's just a little bit more about the gantry sensors. So as I said, data generation is a breeze for us. On any given day, we can generate up to 10 terabytes. Our typical performance hovers right about 1.5 terabytes of data per day, which is pretty sufficient. So in the right-hand corner up here, you can see the instruments in the box that we have with a 3D line scanner, a FLIR thermal camera. This bank of large LED lights is for our PS2 fluorescence camera. We have our stereo RGB. This is basically 2 cameras co-aligned to create a 3D image. We do have our hyperspectral cameras, the Veneer and SWIR, that are aligned just beside the RGB camera. But we look at the data volumes in terms of what we're generating. For our RGB, a typical scan of the field generates about 550 gigabytes of data. And this equates to about 15,000 images. For thermal, it's a much quicker, faster camera. It generates about 5.5 gigabytes. Significantly less images, about 3,000. The fluorescence camera, it's a very unique sensor. It basically, because it emits this giant flash of saturating light and then takes a series of 100 images, it generates about 80 gigs of images. 80 gigs of data. Then we have our 3D scanner, which is one of my favorite sensors. This one we primarily run at night. And this generates on a full field scan about 300 gigs. And then, yeah, our hyperspectral cameras, when both are running in parallel, we can easily generate 600 gigs per pass. And a note on this is that we don't often scan the entire area with our hyperspectral cameras, primarily because that would be beyond too much data, and then, you know, scanning the alleys and whatnot just doesn't add a lot of value. And again, that's just data that we have to store. So to address this issue, we came up with a software solution called PhytoOracle. And PhytoOracle is an open source, scalable, modular workflow. And why this was so critical is, previously we were using an Internet 2 connection to ship our data across the country to the National Center for Supercomputing in Illinois, where it was sitting next to IBM's, Blue, and there was Watson. But basically, we weren't getting access to that type of computational power. And so that's kind of why it took so long to process these data. And so when I took over, I was like, well, there's got to be a better way. And lucky for me, Arizona is home to an NSF-funded project called Cyverse, which is a giant life science cyber infrastructure network. So basically a giant supercomputer. So I talked to the school, the program manager, the PI of the project, Dr. Eric Lyons, was like, hey, can I start shipping my data here? And he said, of course. And so how PhytoOracle is set up is that we ship all of our data from the gantry from Maricopa, Arizona, down to Tucson, and it goes into the Cyverse data store. From there, a user logs in through the terminal to what's called a manager node. And the manager node is basically like a boss. And the boss that manages all these other worker nodes on the right-hand side. And so what the manager node does is takes, the specific tasks and a subset of data and distributes it across the different worker nodes. So all these worker nodes are connected, and so they kind of communicate in parallel, but basically this just distributes the task across multiple computers, so parallel computing. And so kind of to give you an idea of the scale of how much this increased our speed, so if we look at processing a full day of data, 10 terabytes on a 4-core like lab computer, it could take about 11 years. With our process now, it's about 1.2 days. And so we've actually really worked a lot on our processing speed and computational efficiency, because really the goal that we're trying to get to is real-time data processing. So as the scan is happening, the scan will complete, the data will get packaged up in a tarball, shipped to us, and basically, the next morning I can look at it and we can decide whether or not the scan was successful and the data were good. So why distributed computing is so important for us and why this manager workers and framework is so critical is basically it's to handle the large volumes of data that we're generating. Like I just said, that if we try to process this on one machine or even locally, it just becomes physically impossible. And so with this manager worker setup, we're able to take one task and distribute it to, as many worker cores as possible. So on our HPC system, sometimes that's 100. Over the holidays, you can imagine that bumps up to a bunch, like we can get thousands of workers. And so over here on the right-hand side, you can basically see that, we look at processing time, if we only have, one worker available, it's taking 1,600 minutes just for RGB. But as we add up to these 1,000 workers, it drastically gets smaller and smaller. So that's basically just shows the scale and power of having this distributed framework to really make the data processing possible for us. So PhytoOracle also provides a general use framework. And I recognize that we are probably one of the few groups in the world that has access to such a unique piece of equipment. And so when we developed this pipeline, we realized that we needed to make it usable for other types of data structures. So specifically, we identified, UAVs as primarily one of the major types that we wanted to target. And so when I say general use, basically the requirements we kind of have are having, geotiff images, a GeoJSON file. So those familiar with QGIS or ArcGIS, this is basically a shape file defining the area of interest. And then we use a lot of PyTorch, faster RCNN models. A lot of artificial intelligence is employed in this pipeline to basically speed up the computation and, handle the tasks that are actually needed. So in this case for RGB, we're using a faster RCNN to identify the individual plants. For thermal, same thing, a faster RCNN as well as k-means clustering to figure out which of those pixels are plant and which of those are soil, and those tricky areas right around the edge of the plant where you're not quite sure whether it's plant or soil. Our PS2, we got to work with some really unique colleagues that are experts in this and develop our own pipeline for processing PS2 data. And then another one that's been a real, I guess, challenge for us is semantic segmentation of 3D point cloud data. Although in the image it looks very easy, discernible what you're looking at, from the perspective of an algorithm, they're just 3D points. And it's the spatial relationship of the points that really define them as a feature. And so, with these inputs of GeoTIFF images, GeoJSON, and artificial AI, machine learning and our artificial intelligence algorithms, we're able to kind of develop this framework that we can apply to not just our gantry data, but to drone data as well. We've even tried it on mobile phenotyping platform data. The other thing we're big on is, reproducible science, especially when we're generating this much data, right? Like when you have sample sizes that we're talking about here, it is really easy to get the answer that you want. And so I told my group, I was like, I want to make sure that whatever we put out there, whatever we're saying, like people can test it, they can validate our methods or question our methods and, show us what we're doing wrong and how we can improve. And so one of the key pieces of technology to really pull that together was container technology. So these are Docker and Singularity, but basically container technology packages up the script itself that you're actually developed, but it also packages all those dependencies and is a form of version control. So that way, every time like R or Python updates, you're not having to get locked into, figuring out what the most recent package is or trying to find old packages to get your code to run. The other thing that's nice about container technology, and one of the ways that we have developed it, is I hate to use a phrase, but it kind of turns it into like an app store where we can select. So in this case, we have container ones are pre-processing, container two's alignment, container three's post-processing, segmentation, plant clipping, and then finally, getting the actual trait extraction. With the container technology, we're actually able to plug and play and use different containers where we need them. But more importantly, why this is helpful is for other users, some of the tasks that we have to complete for our data aren't required for them. So they can just select the specific containers that they're interested in to serve their needs. Additionally, like all of our stuff, so you can take our containers and you can modify them yourself. So, if you want to change the pipeline or build a new features, that's totally possible. We have all of our codes freely available. We're happy to share it. We're happy to help you get it set up. But basically, what this really allows us to do is the stuff that we're putting out, the data that we make publicly available, you can get our containers, you can get our scripts, you can validate it, you can question it, you can tell us what we're doing wrong. I would never sit here and say we've got it all figured out. Again, with the amount of data that we're trying to process and handle, it exceeds what a group of people can really look at individually and like really dig into. So by making it reproducible and open source, we really want to engage the community in looking at what we're doing. So next, I just wanted to briefly walk through some of the steps. Probably not the most exciting thing, but it kind of gives you an idea of all the steps that are involved. So for our pre-processing, right, the gantry is scanning back and forth across the field. It's collecting all these images. So these are binary images that have to be converted to GeoTIFFs. So basically, when the camera takes an image, the metadata that associate the image with that particular spot in the field is recorded. Another thing that's unique about our system is, to most people's surprise, we don't use UTM coordinates. The gantry is all based on an XY axis. Beneficial in some cases, a pain in the butt to work with in others. So we basically have to take those XYZ coordinates, convert them to UTM to basically align all these photos and get them close. So once we have these GeoTIFFs generated, we then can do an orthomosaicing step to create a full field image. Why we want a full field image is basically to make sure we've captured everything in the field and that we have accurate representation of the plants, the plots, and the specific irrigation treatments that we're applying. So okay, so now we have our orthomosaic, and just like with drone processing, we want to hone in on our experimental plots, experimental units. And that's what we call clipping agricultural plots. For some, it's easier than others. So for row crops like sorghum, it's a breeze. The lettuce is more challenging because the lettuce is grown on a vegetable bed, and we have to get 2 lines of plants like right next to each other. So then once we're able to do that, we can clip those plots and we can generate plot level orthomosaics, which we can use for extracting plot level data as well as individual plant data. So here we go with the plot level orthomosaics. So for like RGB and thermal, these sensors provide data that we're actually able to work with on the individual plant level. So basically, the images getting taken up, we're using an RCNN to do the object detection, and then that plant is given a specific location within the field. And so from that, we can look within a plot. We know the plot number, the genotype that's there, the latitude, longitude of that specific plant, and then the bounding area or whatever phenotype we're interested associated with it. Same thing with thermal. Basically, again, using the k-means clustering to separate plant from soil, linking up those same things. And then for our plot level data, which is mainly just the PS2 camera, basically the PS2 camera is taking the image of that whole plot. And this is probably more traditional to like a UAV processing pipeline where the individual plot, genotype, and the photosynthetic parameters are associated with that one plot. So what gets tricky is, every time we do a scan and we process the data, we're generating this giant flat file, and what we're doing is over time, we're just building this in terms of a z-axis towards us. So we have time point 1 through 4 up to n. So we're using a glometer of clustering to basically align the different plants over time so we can track the same plant and make sure we're getting the same plant. Because that was a huge concern of mine, is that the spatial resolution that we're trying to achieve with something as small as lettuce, it's really challenging. I wanted to make sure that each plant that we were analyzing over time was the same. And that's just kind of how we did it. And so once we have these data, it gives us a unique time, aspect of watching the plants grow. You can see, obviously there's aberrations within the thing, but for the most part, we get a very nice growth curve. And when I talk about the challenge of identifying single plants and tracking them, this is a lettuce plant just emerged. This is about the size of a dime. And so I want to be able to track that dime-sized plant from dime all the way to a giant head of lettuce. And I want to make sure that that plant, we're looking at the same plant every time we take the measurement. And I also want to make sure that, besides just our RGB, I want to make sure we're capturing with the thermal and all of our other sensors as well. So this was not a trivial task for us. So initially, when I started the project, I assumed that because this was on a fixed moving system, that every time an image was triggered, it'd be looking at the exact same spot in time. It was sorely wrong. It turns out, when this gantry is moving up and down the rails, sometimes the two sides of it get alignment. Additionally, that giant sensor box is like a pendulum. So when the wind starts to blow just a little bit, it starts to swing and rock. The triggering of the camera as it traverses the field going back and forth creates what you see here on the left-hand side, where every single pass is out of alignment. What became even a bigger problem is commercial stitching software like Pix4D doesn't handle this. So most drone softwares require 70–80% overlap between images, and that's a significant amount. Our gantry, when I took over, was set at about 15 to 10% overlap. So basically meant that there's minimal features to align with. And when you look at early season, it meant that there's really hardly any features outside of dirt. So this was a challenging problem. And so we worked with some gentlemen in the computer science department, Arian's here, basically said, hey, is this an interesting computer vision problem? He said, absolutely. So he ended up developing his own software called MegaStitch. that's just like Pix4D, but operates a whole lot faster. And so using this tool, we're able to now, basically create orthomosaic. And if you look here, like here's a whole field on the right-hand side, but when you zoom in, MegaStitch is actually able to get those leaves so perfectly aligned, you can really have a hard time telling the two images apart. Even when we use like Pix4D or Metashape to do the same thing on just like a small set of images, it couldn't match this level of accuracy. So it was really cool to see, this problem that for a while ruined my month, turned into like a new opportunity. And it's been, a critical piece because for our processing pipeline, we really do rely on the RGB for providing a lot of the geospatial coordinates that were used for the rest of the processing. The other thing that was beneficial about MegaStitch is we have environmental constraints. So on the left-hand side, this is what it looks like when a scan's going on and clouds pass by. We get these large areas of shadow highlighted by like super bright. Arizona is one of the highest intensity, highlight intensity spots in the world. Right next to us is Yuma, which is the sunniest spot in the world. So that was a problem. The other problem is that the gantry is such a big physical structure with that cross member and top part that it casts its own shadow on the images it's trying to take. That's another discussion with regard to like the instrument design. But again, this was a problem for commercial software. Metashape, Pix4D really struggle with the illumination problems. But again, this MegaStitch was not an issue. And so this was really kind of a breakthrough moment for us because it allowed us to develop more of our pipeline and tools. So the other issue I kind of already mentioned was identifying and tracking, 30,000 individual plants. That's pretty tough. And so we had another, Travis was an undergraduate when he came to us. He worked on this problem and basically developed a faster RCNN to identify the plants and cluster them over time. And so in this middle image, on the far left is an individual scan, and his algorithm is, we found the plants, we have their approximate coordinates, and then the question is, we build that flat file, how do we make sure that, the plants are the ones that we think they are? And so he worked on this for quite a while, but was able to develop this algorithm that could line up these plants, and you can see these dots are basically what are computed to be the known location of the plants. And so here, we're tracking the individual plants. We know the genotype information. We know the precise location in the field. And this got me super excited because for the first time, it allowed us this opportunity to actually like watch plants grow over time. And I mean, they're not the best videos, right? Because they're RGB images. But you can see like these are plants emerging out of the ground, again, going from a dime size all the way up to a whole head of lettuce. And although this is cool, what I was really excited about and what I've been kind of after my whole career is for the first time we have this way to track plant growth. But more importantly, in this experiment we were doing, we had different levels of irrigation treatment. And so we can link the plant growth to the environmental parameters that are happening across the growing season. Lettuce is nice to work with, I won't lie. I mean, in terms of phenotype, it's a giant ball on the ground. Additionally, lettuce is one of the few plants that has an exponential growth curve because basically once it gets to the top of the curve is when you harvest. So lettuce was fortuitous in terms of helping us to build this pipeline and basically piece it together and work through. It was a very nice model system. But this was really exciting because this is one of the first times we were able to look at plant growth as it relates to environmental constraints. So obviously in the winter, that's not as critical because it's not as extreme environment, but when we look at sorghum data from the summer, it becomes much more enlightening. Other things we were able to do is basically look at canopy temperature. So as a proxy for somatal conductance and transpiration, as we expect, we had 3 treatments going on. We had a well-watered, a water limited, and a severely water limited. Because it's winter time, we don't always get the stress we want because it does rain and it's not as hot in the winter. So these 2 treatments kind of perform similarly, but the severely water limited definitely had less canopy temperature depression. And here you can kind of get an idea of what a thermal orthomosaic looks like. It also kind of highlights the challenge of finding the plants. Although it looks simple, you know, that it's just shades of gray. From the perspective of an algorithm, it's much more challenging because it lacks some of those features that you get in RGB. Another one of our sensors, this PS2 camera, is very interesting. So basically, it quantifies photochemical efficiency, or how well plants can convert sunlight into biomass. It's a very powerful sensor in terms of its ability to detect stress early on. You know, damage to the chlorophyll happens really fast, and basically it gets damaged before you see any visible symptoms showing up in the plant itself. So we're able to use this sensor over time and track our drought treatments. These data are a little wonky because basically this was a little experiment I wanted to do at the end of the season. We had already finished collecting, and then I just started manipulating the drought treatments to see how fast they would respond. So basically, I took the well watered, and made it a drought treatment, and took the water limited and made it the well watered to see how fast they would converge. And basically, you know, we're seeing a pretty rapid response and recovery for the water limited versus the well watered. This kind of gave us a good idea of like how fast this PS2 sensor can really detect abiotic stress. And sorry, in the image, I should clarify that the areas of like bright red, green, these are areas that are most highly photosynthesizing, whereas purple means it's soil, you know, nothing's going on. The sensor, although it's very cool and powerful, it does have some, you know, limitations in respect to proximity to the sensor, to the LED lights, and to the center camera. That does impact the signal strength. So right now we're trying to kind of develop a more sophisticated algorithm to basically correct for that distance from the sensor to the plant to see if we can get a little bit more refined data. Then finally, the 3D stuff. Again, one of my favorite sensors. It's proved quite challenging. And that's because we have two line scanners, similar to a LiDAR, but not the same principles, looking at the plant. And again, these are scanning as the box is moving, so it creates these compound images which don't always perfectly align. So that's kind of problematic. And as I mentioned earlier, you know, the data that's coming off this are just 3D points. So when the algorithm is looking at it, there's not a lot to go off of in terms of features, right? It's all about proximity and who's, you know, what point is next closest. So it took us quite a while to develop a segmentation model that basically we could feed it a point cloud, and it could tell us, you know, this brown, this is your soil, and things above it are the actual plants. And, you know, in this bottom one, you can kind of see this where we're getting a nice full structure of the plant. And this was not trivial, we found out. Point cloud tools are not that well developed compared to like RGB. Everything was in beta version, so there was a lot of trial and error. The team really, you know, had to pull together to get something to work, but I'll show you in a bit. It's really coming along quite nicely. But with these data, again, we're able to track the plant growth, but also the features of the plant, the morphometric properties. And again, one of the things we're interested in is, you know, can we use these types of data to predict plant performance? So not just like using all these data for, you know, genetic mapping and studies of that sort, but is there an application in terms of, using these data to predict plant performance in the face of the environment? And so I had a postdoc working on this, and basically he was able to use these data, and this was just from bounding area, to predict yield. So here was the true value of the green box, here was the predicted value, and the task was, if you know, you could only use data from the beginning of the season to about 2 months, and then basically don't use any data in here, and can you predict that final outcome? And the reason that was of interest is because lettuce producers, as they price their field, if they can grow it for 2 months and figure out whether or not they have an economically valuable crop, that's what they want, because if they're not going to make that yield, or if they're not going to have a buyer in a month, they'll just plow down the field and start again. So that was a nice tool that we developed. And then Just to kind of conclude, Oracle addresses kind of three major concerns. So data reproducibility, so this container technology, so that basically people can evaluate our work as well as their own work. Scalability, using HPC, using computer resources to scale up the data processing itself, and extensibility, so not just working with gantry data, not just working with one type of data, so RGB, thermal, fluorescence, 3D. The hyperspectral pipeline, I will say we are actively working on it. I just don't feel like it's prime time yet. And again, I would just conclude with saying, this pipeline is not just for gantry data. It works wonderfully for drone data, even part data. So just a few summaries as you're thinking about, phenotyping platform. Oracle is a data processing pipeline that can handle various types, not just for gantry data. It really does enable reproducible science, processing data fast and efficiently. Season of data, we just did this a week ago. So we processed an entire season of data in 3 weeks from start to finish. Additionally, we've also done automated real-time data processing. This is my favorite part because a scan happens and basically I get a Slack message that says, hey, your data's ready if you want to look at it. So that's nice because it allows us to QC our data and catch problems. So in case our team left the lens cap on the camera, we can catch that and take care of it. And then again, I'll just conclude that it is freely available. So now data processing itself isn't that much great. So when you invest this much time and energy into a data processing pipeline, what can you actually do with it? So one thing that we're really interested in is machine learning. But machine learning, for closing that genotype to phenotype gap needs a ton of data, and it needs a lot of data that's labeled well. And so, what we want is to have a sorghum plant that's been segmented out into individual components. So leaf 1, leaf 2, 3, 4, 5, 6, main stem. But to get an algorithm to do that, that means we have to take the image itself and sit there and have an undergraduate or somebody sit there and label it. And unfortunately, this task is one that just scales. So the more people you have doing it was kind of like. But the idea became, is there a faster way to do this so we can develop these really well annotated training sets that we can apply to our real world data? And so I had the opportunity to work with some fantastic people, Frederick Beans at Purdue, who's a phenomenal computer scientist, and James Schnabel at UNL, to basically take this idea of growing our plants in silico. So growing sorghum in the computer, learning what those features are, labeling those point clouds, to learn about the structure of the plant, but to create these training data sets so that we can use them on our own data. In this image right here, this is 10 different simulated sorghum genotypes. You can see bits of differences in their structure. They become more apparent once you zoom in, I promise. So yeah, this is kind of what we're after right now because, what we want is some really high resolution data. I hope this plays decently well. But this is a high-speed version of the program they developed for the procedural growth model. And basically, you can modulate and change every part of the sorghum plant. When you think about internode length, leaf shape, width, waviness of the leaf, how they're arranged with actual phyllotaxy on the plant. And you can see you can create these really extreme phenotypes. And this was critical for us because some of the populations that we've been growing recently are actually EMS mutagenized populations. And so we were able to use this algorithm to create a large synthetic data set of these artificial sorghum plants. And why this is cool for us is that, the plant is generated in silico. So as the algorithm grows the plant, each point that it's adding, it knows what it is. It knows whether it's a leaf, stem, panicle. And so as these plants are growing, the data points are pre-labeled. So I don't have to spend my time and energy having my team go in there and be like, this is a leaf, this is a leaf, because that takes forever. So now we have these synthetically labeled data sets, and we can apply them to our real world data. So once we have this model trained, we can feed in our data that we're getting from the gantry, and the model can sit there and segment out first the individual plant. Once it has that individual plant, then it can segment out the individual components, like the leaves and the stalk. And so this procedural growth model, again, we are able to generate any type of sorghum plant that you can imagine. Really wonky ones, mutants that you would never expect to see. And because of that, it takes capacity to generate, very varied training data sets. We can basically encompass the phenotype space that sorghum can occupy so that we can use it on our real data. So here's kind of like what a field-grown plant looks like. Colors, emerging from it, obviously, but it has this compound structure, the large leaves. And so here is just the main part of the plant. Basically been used. We have so this panel B is not the real plant. This is a synthetic plant, but you can see that it's labeled. And so what we're trying to do is extract things like leaf width, leaf angle, leaf length, as well as properties of the plants themselves. And so here is the real output. It doesn't look as clean, mainly because we're trying to make the graph and get all the points on there. But in this instance, all these labeled colors are individual leaves that the model has picked out from the segmented plant. So now we can take these and create these wireframe meshes of the individual plant organs. So once we have this is now what we can feed into an algorithm we're working on to extract those features like length, width, curvature, waviness, and other parameters. And so this is what gets us to those really fine scale phenotypes. Another thing that we're actively working on, because we have this high resolution 3D data, is describing the structure of the plant. So we have a torus and circle, pretty similar shapes, but they're not similar at the same time. One that occupies a 3D space and has a more complex structure, whereas the circle doesn't. Using topological data analysis basically is a way to create these persistence graphs that describe the structure of the shape. And so we can see that here, this black oval is made up of hundreds of small black points that are very nice and neat, whereas red creates more of that 3D structure, but it's a lot messier. And so these persistence graphs can tell us, the birth and death of the point. The mechanics of this, I guess, are besides the point, but it gives us a way to identify underlying structure that's similar. And so these TDA features allow us to describe properties of the plant, in addition to just the morphometrics, so height, length, volume, width. Those are morphometric properties. But with topological, we get more of the intricate shape, like how plants like sorghum, some are more like columnar and how it necks down. Some actually grow up and get bigger at the top. And so now we have a quantifiable way to actually describe that shape, in addition to the morphometric features that we hope to extract from like the single leaves that we're pulling out. We're really excited about this. We've done some preliminary analyses, and we can validate that the TDA features are explaining more trait variation and actually help us with predicting what the plant genotype is. So it looks like this is very valuable data and insight, and something that wasn't previously available based on non-Phenomics data. So finally, this one's kind of out there, and I admit it's probably more eye candy than utility. But one thing we're really actively exploring is moving our field environment to virtual reality. Not to like rip off Mark Zuckerberg and his lame metaverse, but VR, we think, represents a way to have people interact with data in a more native state. Humans, it's shown that humans are good at picking out patterns and features in visual data versus just like looking at a spreadsheet. So this is a lettuce diversity trial that we grew. This encompasses basically all the known phenotypic variation for lettuce. You can see here that you've got black, green, different leaf shapes, leaf types, market classes. And so I'm going to share this video. Here's a link to the video. I'll share just because it oftentimes doesn't come through. So this is a reduced representation of our lettuce field. Basically, it's reduced because if we put the whole thing in there, it just bogs down because it takes so long to render. But basically, you put on the VR headset, have the hand wands, and this is your field book now. So you're walking through the field, and you can walk up to a plant. You click on this, you can select the plant, so you point at it. When you do this, it triggers, it goes to the database and it pulls all the associated data with that plant. So we can look at its growth curve. You can look at the thermal data that's been collected. And then furthermore, if it's, something interesting, its shape or whatever, you can look at the individual point cloud of that plant. And while, we showed this to the Department of Energy to just kind of like show them, what's possible with rich data sets like this, we quickly learned that people that had no idea about lettuce could actually start to tell differences. And they're like, oh, like these two are different. And, for somebody like me that's around the lettuce the entire season, I could just intuitively tell you like, yeah, because I know it. But somebody who's never been to our lettuce field kind of presents like a new view on what the plant phenotype really is. And so when you let them walk through a VR field, they're looking at different things than I am. And so we found it to be kind of cool in terms of what people pick out. Is there utility and value in this? Hard to say. I think it's cool. For the summer, it's nice because not everybody wants to travel to Arizona in the summer when it's 120. So this is a nice way for people to put on VR goggles and get that field experience without actually having to feel the real field. So just some thoughts and conclusions about, kind of the Phenomics data processing pipeline and, really the value in these large scale platforms is first thing is investing 30 to 40% of your hardware costs in data processing and analytical pipelines. The initial team didn't do this and it kind of showed, like they didn't have the ability to QC their data. It took 9 months to process. And it just really made the whole instrument itself unusable. And so, having to go back, basically start from scratch and build this pipeline, it took us, 2.5 years. And that's why I'd say the next thing is, for budgeting project timelines, kind of the same fashion from when you think you're going to go from data collection to actually doing science. That's probably been the most painful thing for me is that I am not inherently a data person, I guess you will. I prefer just to analyze it, not doing all the processing. And so I would just say like to kind of keep that in mind as well. Budget for data storage, and more importantly, the intermediary products. So as we're going from raw data to our extracted phenotypes, there's a lot of files that are generated in between. As scientists, it's ingrained to us that we're going to keep everything. And I can tell you personally that I can't afford to keep up everything. So processing a season of data, so about, I'd say about 150 terabytes of raw data turns into about 580 processed. And so for us, we are actively looking at basically we're going to keep the raw data so that we can always go back and recreate the products that we might need, and then just storing the extracted phenotypes. Another thing would be if you have access to distributed computing or HPC resources, they're kind of a must. I've tried doing this on local machine workstations, even small servers. It doesn't really scale, and you can't really leverage the full power of the technology if you're compute limited. So that's why I would say, as you think about investing in systems like this, to make sure you have the computational resources to really process and leverage the data. So I also believe, though, once you achieve this, that high resolution phenomic data, it does have a lot of potential. I'm really, really excited about, that 3D stuff and being able to look at 30,000 plants and pull out the individual parts of the plant to study those features and to understand, why an EMS immunized sorghum plant is so much different than, the wild type. And specifically using those differences to look at the genetics to understand, how that mutant's responding to the drought stress that we impose upon it, but just to also understand, why that plant is different. And then finally, as we look at TDA represents kind of this buzzword of latent space phenotyping. Latent space phenotyping basically being things that humans ourselves don't identify as phenotypes. Right, because up to this point in time, a phenotype is a human-defined feature, but there's lots of ways to describe structure and function that are beyond us. So, using these different kind of quantitative metrics has been enlightening. They do have they do capture variation and have, I think, some significant value. So anyway, I wanted just to conclude with, thanking the entire team. This has really been a lot of work. When I started this as an assistant professor, a lot of people told me it would end my career. Maybe it has. But, it's been a fantastic project to work on, to learn with. Couldn't ask for a better group of people to get to work with. And for myself, learning something new. I mean, naturally, I would have never gone into something like, data processing unless I had been forced. And I'm glad I had, because it's really opened up my eyes to kind of, the challenges that plant science and all of science faces in the future with respect to this like data tidal wave. I think people often call it drinking from a fire hose, and kind of what the challenges are associated with that. So with that, I would thank you for your time. If there are questions, I would be happy to take them.
Thanks for that, Duke. I think that would have broken the lesser man, to be honest.
Still could be broke, man.
Yeah. It's interesting, that bit right at the end where you thought it was more a showy thing than anything else. I was chatting yesterday to breeders about the application of digital twinning in breeding, and I could really see that coming forward. So you make a lot more mistakes on computer. So, and what's driving them is cost reduction, just completely, and de-risking and investment and so on. And I think we'll see that coming in.
Definitely. That Science and Technology Center I'm part of, like, that's what we spend a whole day on, is how do we use digital twins? Because, the breeding process is so lengthy and resource intensive that, fail fast and fail cheap. Yeah. I think that VR component is something that we can do.
Yeah, I mean, it won't look like that, but it's different algorithms for predicting it. I mean, it's almost going back to a very old program, a very old film. It's a plant breeding equivalent of that film War Games. It's scenario planning just again and again and again.
Pretty much.
Yeah. Okay, so I'll open it up. Has anyone got any questions? I've got several if you're stuck, but I'm sure there will be some questions. Feel free to stick your hand up or just shout out. If not, I will ask one.
Can I start just with a quick technical question, Derek?
Ian, go ahead.
So I run our local HPC here, and I mean, a lot of the stuff you talked about there sounds very applicable for us to sort of like literally just take that and dump it into Dockers and Singularities and everything else. So I haven't touched Cyverse in a long time. We have Slurm. How compatible would it be?
So full transparency, I'm probably not the best person, but we do use Slurm. So I think this has been run at the Texas Stampede Supercomputer Center, and I believe that's how they did it. So I can get you the specific.
It sounds like there's probably a really strong chance we could literally just take it and probably get it up and running quite quickly. Yeah.
Yeah. Because I do recognize Cyverse is kind of like our unique thing, and they use iRods, which is a pain.
Yeah, for storage.
But yeah, so people have asked us about Slurm. But yeah, I think it should be fairly close to plug and play. Well, but yeah, if you're interested, I'd be happy to follow up and get those resources to you.
Yeah, I think I mean, we've got 3,500 cores, so definitely worth trying it.
Definitely.
Sounds good. Okay. Any other questions? While you're thinking of one, it's interesting you had to go down this route, developing all that stuff. Is that indicative of Lemnitech's embedded stuff just ain't delivering?
Yeah, so it's a complex thing. I'll be forthright and honest. I have no love for Lemnitech. Yeah, they sold us a turnkey package, right? And in reality, they had never built a system this big. So the first 3 years, they were just trying to get the gantry to run, and then once they had it running, they realized they didn't have any algorithms. They realized they didn't even know how to process the data. So all this was happening, Derek, and then I cut them a check for $250,000, and then they filed bankruptcy 48 hours later. Yeah, so basically once that happened, it was the writing was on the wall that it's just done with LumdaTech. They've since been rebought by another company, but they've retained their entire leadership team. So when they reached out to me to ask for more money, I politely told them no with some more colorful language. But that's really what necessitated it, was just realizing that LumdaTech doesn't have the support. And so when they went bankrupt, I actually hired their lead engineer, because I realized without this guy, like, I would not be able to run the machine. And I've had probably 11 different people, owners of LumdaTech systems, like universities, reach out to basically be like, we have a system that we can't make work. And even if we can get it to work, the data sucks.
I think
Can you help
a lot of
us?
us have heard that kind of problem before.
Yeah,
I mean, the area is still quite nascent, to be honest. And
it is.
the scale you're at is just astronomical compared to that. So
Definitely. And people always ask, like, would you build another one? You know what? My honest answer is probably not. They always, the DOE called it the Hubble telescope of agriculture. And I was like, that's a bit of a strong word. But I do think it's a useful tool and it has merit. But yeah, definitely, it's a large investment and whatnot.
Cool. Any other questions? So I'll ask one if people are thinking about them. Are you moving forward to integrate other assessment technologies? So like repeated transcriptomic analysis at certain points. I mean, it's adding just more to your data load, obviously, but potentially the exponential lift in utility in that combined data.
Yes, so that is one of the reasons why we've pursued a rewrite of the entire software that runs the machine, because basically the LumdaTech software wouldn't allow us to integrate new sensors. So that will be completed at the end of hopefully November, at which point we are looking at getting some more sensors like solar-induced chlorophyll fluorescence sensors. There's some new emerging thermal imagers that we're interested in. But yeah, basically to improve the utility, because we do offer a really good test bed for sensors, because you don't want your $300,000 sensor on a drone to crash. And so we can put on the gantry in a controlled environment and kind of validate it. And we've done that with another hyperspectral camera from Resnon, and it worked really well. And so that was one of the utilities we see is just trying out new sensor hardware.
Yeah, I mean, that area is evolving where you're getting sensors coming in to predict quality and nutritional value of the crop. Whether it's near IR, whether it's chemotypic membrane-based systems, that might be a bit harder to put on yours, but the near IR one on a laser-based system would be a really neat one to put onto that.
Yeah, we've also talked to some colleagues about doing some soft robotics to do the plant tissue sampling. That's obviously down the line, but just kind of to suss out whether or not it's even practical to think about it.
Sure. The data you're collecting then, right, we've got a couple of questions coming. Dominic?
I was just going to ask, how do you judge in terms of how successful? Because presumably you could change something downstream, and then this is always something. So I've been doing field imaging for a while, and you kind of have all your steps, and then you suddenly realize you want to change your back step, but then it's very difficult to judge how successful it is in achieving a better outcome, I suppose, and what do you judge as a good outcome for the data processing?
Sure, I guess my answer to that would be, you're right, because we've kind of just built this pipeline, finally have it all running. How much like tinkering and improvement have we done? I'll be honest, like not a ton. Mainly right now, the test I use is, with the extracted phenotypes from the images, what's the heritability look like? If it looks garbage or turns out to be a 0 in some of our traits, I'll be honest, like they're not always great. One that we have a struggle with is convex hull volume. With our lettuce, it feels like it's capturing too much of the soil, but or they get weird inflections from the shape of the plant, and the heritability is kind of garbage. And so I guess at this point, that's how I'm approaching the QC and like knowing whether or not those are usable data. I hope that answers your question, Dominic.
Yeah, that's it. Yeah, we have tried similar things. If we can map the data, it must mean something, even if we can't map it, it's no use. Yes.
Yeah.
So, Colin, you have a question?
Yeah, thanks for the talk. It was really interesting. I was just curious. There's a lot of soft fruit work goes on here, and obviously the focus there is on not every part of the plant. Is that something that you think this setup could actually get to in terms of processing the imagery, with actually focusing in on the fruit part of it?
Oh, so yeah, with the sorghum panicles, I see that's what you mean. Like that's one of the features we're looking to extract. So can we get the actual panicle volume? And then with that laser line scanner, the resolution, depending on the scan height, can be sub-millimeter. Some people have thought, well, if you can scan with that high resolution, can you count, the number of grains? I guess I'm optimistic that maybe you could, but I think you could get some, pretty good data, probably similar to like what apple breeders are after in terms of height, width, volume, some of the shape in terms of describing it. I think we could probably get some of that, but high res, I guess, remains to be seen.
So have you applied it to tomato? I saw on your website you're working on tomato, so that would be a great analogy for this.
No, growing tomatoes in the desert was extremely challenging.
It did strike me as a bit odd.
Yep, I've tried a lot of things, including rice. And basically with how much it costs to run the scanner and everything, I got to make sure the plants grow really well.
No. So maybe to close it, because we've got one left here. Fraser. Go ahead.
Oh, sorry. I apologize strongly.
Can't really hear you very well, Fraser. You there?
He was on the train. That's probably why he's coming through badly.
Okay, he's gone through a tunnel. Try again?
You hear me now?
Kinda, yeah.
Kinda. So it was just a question on the sort of processing from the gantry to deal with shadow. I've actually worked on some of the data myself. It was the Final Grain Visual Categorization Challenge in Chicago this year. And a lot of the issue was sort of dealing with the occlusion from the shadow in gantry. So how do you sort of manage that and illumination outside in general? Is it just a case of, you image on days where you're going to get less shadows, or image at a certain time where the gantry isn't present, or is it all post-processing?
So if I understand the question, it's how do we deal with the shadows and
Yeah.
So excellent question, Fraser. So the shadow changes obviously with the time of year. So typically May, June, we get pretty good scans without that heavy shadow. July rolls around, it's pretty brutal. Right now we are working on trying. So initially the box came with a set of halogen lights. They just couldn't hack it. Arizona is a super highlight environment. And so basically we estimate that, there's about, I think it's probably 3,000 micromole of sunlight coming down. So to get illumination on even imaging is tough for us, but we are trying it. We're working with a company called Hyphen. Maybe you've heard of them, but they have some technology. So we're working with them to see if, we can kind of reduce those shadows, because I think it's kind of a fundamental flaw in the design of the system. And I do think it compromises our data when we try to look at things like disease phenotyping. Basically, those shadows hide a lot. And, can we overcome that? In terms of post-processing solutions to that, it's really tough, because if you zoom in on those images, it's kind of the worst case scenario, because you have super dark with overexposed. And as you try to do any type of white balancing, you lose one. So we are all ears if people have, we've tried the giant shade around it. That didn't go so well. So yeah, it's definitely a challenge, and you know, I recognize that's a significant limitation of the instrument, is that all the sensors are directly underneath the box. We did move our thermal camera outside because it was just such a bad design. So our thermal camera is positioned about 1 meter away on the south side so that it's, you know, always seeing plants that have never been shaded. But yeah, it's definitely a problem.
There's never a non-problematic system. I think that's the thing. So Fraser, actually, if you've got some ideas, just chat to contact Duke. Coming to an end here, one thing I was going to talk about just briefly was you're acquiring huge amounts of data. Do you plan to do something with it like the human data system is, so you let the data wild into the environment and let other people play with it?
Absolutely. So that's already happened. All of our data is publicly available.
Cool.
I'm happy to share the links. Unfortunately, it's in cyber, so you have to, I shouldn't say unfortunately, but you do have to create an account. So the data's out there. We're happy to work with people. We have groups, UC Davis, a group in Purdue, another in Danforth. So we have people that are using it. But yeah, we'd like to see, you know, broader adoption of it, just because we put so much time and energy into it. And then the genetic data, I think the EMS populations, that data is also available. You know, initially, I think some of the PIs were, you know, you're always worried about getting scooped or whatever. And I just told them, I was like, with 500 terabytes, there's a lot of science to be done.
Yeah, there's enough there for everyone, I think.
Pretty much. I was like, you know, we're never going to be able to analyze all of it.
No.
The program officers don't always like to hear that, but I don't know.
It's just good to see it. Good to see data being used. I mean, that's an interesting bit that comes from talking to industry. They acquire huge amounts of data, and I reckon they'll use 10% of it max.
Pretty much. And yeah, I mean, we're always, I mean, people reach out to us, and I'm always happy to be like, hey, you know, we'll help you get what you want.
Okay, that's been really illuminating for us. Horrifying by the same turn, I think. But we're not going to build anything to the scale you've got. I'm sure we will be back in touch. There's a lot of commonalities what we want to do. So if everyone could just thank Duke in the usual manner, and we'll let you free to probably go and have breakfast now, actually, where you are. Oh, no, you're in New York, so it's 5 hours, so you're okay. Right? Thanks very much. And
thank you, everybody.
We'll chat to you again.
Bye.
Thanks, everyone. Bye.